As this has been, somebody among you asked me, of course, equilibrium, the problem of finding equilibrium is a preliminary problem, a problem which has to be solved before solving the problem of finding motion. Because equilibrium is a particular kind of motion. One can say in this way: an equilibrium position is a position where, if you place in it the system with zero velocity, the motion of the system is to remain always there, roughly speaking. So equilibrium is a configuration in which the system remains without moving if you place the system in that configuration with zero velocity. So the equilibrium is, in a sense, a particular motion, the motion to remain without changing the configuration. So usually in mathematics you solve first the simplest problem and then you attack the generalization. So if you want to study the vibration of a beam, you start by investigating its equilibrium configurations, then with what you have learned about it, you proceed in learning how to study the motion. Okay? Once more, this is what has been done historically. D'Alembert first studied equilibrium and then generalized the principles to find motion. Okay? Good. Now we must talk a little bit about, we forget for a while about the beam and we try to understand the mathematical problem. How do you find minima in general? In general, you have a function, the independent variable is f, x, the dependent variable is y, you have that y is f of x, and then you say minimum or maximum are such that the first variation of the function is 0 in the neighborhood of minimum of maximum. Let us try to understand better this. You have this point, x0. Okay? Then you change a little bit x0. So you move on the right or on the left. And you have a value x which is close to x0. So your problem is f of x0, f of x is greater than f of x0 if x0 is a minimum. So this is greater or equal to 0 for every x which is close to x0. Okay? So I should write here close to x0. Okay? Because of course the function could do this way. Far, you could have that the value is, this inequality is not true anymore. So we assume that this inequality is true in the neighborhood of x0. Okay. Now, Lagrange was a student who was obliged to find the mathematical equivalent condition equivalent to this, which is valid when the function f is differentiable. And at the epoch of Lagrange, this was rather advanced mathematics. In order to have this inequality verified for every x close to x0, we can write Taylor expansion I know that we are repeating maybe many times these things, but I want to be sure that the message is reaching you, okay? Especially because now we must repeat this reasoning here. I know that also Luca Placidi was telling you these things, but as these are very fundamental, before we teach you more general theories, it is better that you become master of these ideas, okay? And to understand the ideas, the simplest case is the most suitable one. Plus f second x0 over 2 times x minus x0 squared plus other terms. Okay? Now, imagine that you know that the second derivative is positive in x0. This is always positive. So this quantity is always positive. We assume that the other terms can be neglected, are small, so they are not relevant. So fx minus fx0 can be positive only if f prime of x0 is vanishing. Why? Because imagine that f prime of x0 is positive. X minus x0 can be negative if x0 is smaller, x is smaller than x0. So this dominant term kills this positive value and makes this inequality impossible. Vice versa. If f prime is negative, then with x greater than x0, this quantity becomes negative. So the only possibility for our function f to have a minimum in x0 is to make this term dominant, and to make this term dominant, f prime has to be 0. This is the discovery of Lagrange, mainly. I don't know if in your country you call it theorem of Rolle-Lagrange. Do you have heard about Rolle-Lagrange theorem? Okay, you know, in Anglo-Saxon tradition they call it with different names, so it could be that you follow one tradition or another one. Okay, so the main idea is the following: to find minima. Try to follow the reasoning, because this reasoning has been generalized by Lagrange to this energy. I take the f minus f0 increment. This we call it finite increment. I approximate it with the linearized increment. Why I call it linearized increment? Because this is the best linear approximation of this increment, which is valid when x is close to x0. So this linearization of the increment is obtained neglecting all other terms in the Taylor expansion. Now, the linearized increment, or the small increment expression, or if you want, the differential of the function f, is 0 when you have a minimum. Because otherwise, it is not possible that this animal has this infinite increment has always a positive value. You know, linear functions change the sign. This is the problem of linear functions. They are either positive and then negative, or negative and then positive. So linear functions are to be 0 in a minimum. Linearized increment must be 0 in a minimum. Okay. Now this is true for one function, real function of one real independent variable. Now our problem is that we must understand how to generalize this with the energy. Now, which is the true problem for the energy? The independent variable is not a real number. The independent variable is a function. This is the true problem. And for this reason, Euler did not manage to find alone the solution. So let us try to understand. This is U star. U star is the equilibrium shape of your pin. Which is the value for U star? U star has to be such that if you change U star adding it delta U, of course delta U of capital S, U star is of capital S. So you change a little bit the function. This is the big problem. The unknown configuration is a function. You change a little bit the unknown configuration. How you change it? Adding another unknown function. So you change a little bit the unknown function, you get another function, and the total energy must have a greater value for every delta U you are adding to your U star. The really difficult thing to understand here is that instead of having a real variable or n real variables, your configuration is a function. You know, mathematically speaking, this is a nightmare. What it means that two functions are close? This is not an easy problem. When you write this equation, what it means that x minus x0 is close? Their difference is small. There are two numbers, you calculate the difference, and if this difference is less than 1/10, you say they are close, or less than 100, 1/100, they are close. Now the big problem is, what it means that two functions are close? I know that you have already heard a version of this lecture. I wanted to repeat it to you because I want to send you a message. The message is that you must go deeper and deeper in your understanding. So, you have this function. Then I have this function. The values of these two functions are very close. But if you calculate the derivatives of these two functions, the derivatives are very far one from the other. Do you want to say that these two functions are close or not? In your energy you have the second derivative. So what it means that two functions are close? In the context of the theory of Euler, two functions are close if their values are close, the derivatives have values which are close, the second derivatives have values which are close. Now, what is very surprising, what astonished me a lot, is that the mathematical rigorous theory teaching us what it means that two functions are close has been invented by Sobolev, a Soviet scientist who was active in 20th century. Lagrange did not know the theory of Sobolev, but he applied it in the right way. He managed to deduce a condition for minimality, which is the right condition, without having learned the theory of Sobolev spaces. Or, in a sense, he was inventing parts of the theory of Sobolev. So, he knew how to calculate the first variation of this energy, assuming that two functions are close when their value, the value of their derivative, and the value of their second derivative are close. Okay? Now I explain you the trick he used. So I have integral of km over 2 u second, u plus delta u second, minus integral km over 2 u second. What I'm writing? The finite variation of this deformation energy. Okay? This calculation probably you have already seen by Luca Placidi. Okay? I want to reinterpret it, adding more details and repeating it another time. Now, what it means delta u? delta u, delta means that the variation is small. Okay? When I write that this is equal, sorry, of course here I must write square. Okay? I have the square there. So I start writing this, u second plus delta u second. Then I change and I place the second here. What I'm telling is that the second derivative of u, of delta u, is small. Okay? So I am assuming that I am adding to u a delta u, this delta u has a first derivative, delta u prime, and a second derivative, delta u second, and three of them are small. So I can neglect all of them. Delta u prime, delta u second. Lagrange wrote about 20 pages for persuading the reader that he needed the commutation of delta with derivatives. So in a sense, he was already formulating the theory of Sobolev spaces. Okay? Now let us see what happens when this commutation is possible. Now I go and develop this square. So I have u second square plus 2u second delta u second, and now I don't write the brackets because delta and the second derivatives are commuting, plus delta u second square minus u second of square. Now I should write in a better way the brackets. If I place these big brackets, this animal is not there anymore, otherwise everything is wrong. This is the bracket. Here I have km over 2, and I have the integral. Okay? I'm not writing ds. Okay, now this cancels with that. This is the square of a small quantity, so it is negligible because we want linearized expression for this. So this finite increment is equal to the integral of km over 2 times 2u second delta u second. Okay. Of course, should I calculate the first variation of this? It is useless because this is a linear quantity. So the first variation is integral of bs delta u, and the variation of this is fl delta ul. Okay. So at the end of the story, the most difficult first variation I must to calculate is this one. Okay. Now I think you have seen the subsequent calculations. So I will run, but I need to underline some parts of this subsequent deduction. The main idea of Lagrange is to integrate by parts. So this 2 goes away with that. So we have integral of Km u second delta u second. Okay? So this is equal to integral of what? Km u second delta u prime prime minus Km u second prime delta u prime. If you calculate the derivative of this, you have the derivative of the first factor times the second, which cancels with this. Then the first not derived times the derivative of the second, which is this one. Okay? Integration by parts, you should know. Okay, you have seen it already, so I can run a little bit. Okay, then this is called Torricelli theorem in Italy. I don't know if you call it Torricelli theorem. The integral of the derivative is the function calculated on the integration endpoints. Okay? Minus integral of Km u second first delta u prime. Okay? So you discover that you have some boundary terms which appear naturally in your integration by parts. This is the reason for which you need to apply boundary conditions in the theory of beam. There is no physical meaning of this. The interpretation of these boundary terms is obtained a posteriori. It is not a priori, it is a posteriori. You integrate by parts, you get these terms, and you ask yourself, which is the meaning of this? Okay. Then you keep integrating by parts. So this is equal to okay, it is better if I place plus here, minus inside. So I write Km u second prime delta u with a minus sign here, prime. Okay? So when I calculate this delta u prime, I get exactly this one. Okay? So I need to place here plus Km u second delta u, because in this way I calculate this first derivative here, and it goes to 0 with that. Then I calculate the first derivative here, and I get exactly the other term. Okay? Now, Torricelli again. And I get 0L, and I'm left with this integral here. So the first variation of the deformation term of my total energy is given by this quantity. To this first variation, I must add the first variation of dead loads applied. Okay, so I erase the calculation terms and here I have minus BUS, okay, delta US. This is the dead load term we have, and here I have minus F delta UL. This has to be 0 for every delta U. The poor Lagrange did not know when he started doing these things, Lagrange theorems. He needed to invent them. So I am revisiting these results because I want to show you how many ideas from mathematical analysis were developed in order to proceed in these calculations. So, the equilibrium shape U must verify this equality to 0 for every variation delta U. Here I have a plus, of course. When this equality is equal to 0. So, find the function US such that for every delta U, this is equal to 0. This is our problem now. Okay? If you remember what we have said about Archimedes of Tarentum and the equilibrium of a lever, this resembles very much the principle of virtual work. For every virtual displacement delta U, the external work and the internal work must, once sum up, give the result 0. Every virtual displacement makes the total work vanish if you start from an equilibrium configuration. So, slowly we are understanding how, why, and how the principle of virtual work has been conjectured as a generalization of the stationarity condition, as a generalization of the condition that the energy is minimum in the equilibrium configuration. Okay, now I have the interval 0L. Okay? And I have the integral between 0 and L of a given quantity plus some quantities evaluated on the boundaries, and the sum of these terms has to be 0. Okay. Can I use a delta u like this? I start considering delta u, which is 0 with all its derivative in 0, and 0 with all its derivative in L. Why I'm doing this? Because I want to get rid, for the moment, of these boundary terms. Okay. Now, Rafael, you understand why it is very important to talk about the quantifier for every. If this is true for every delta u, it is true also for particular delta u. Okay? The famous Persian mathematician Algorithmi, he knew the meaning of the expression for every, and he was applying it very carefully. I don't know why many of my students nowadays tell me they don't understand why, if something is true for every delta u, then I can choose this particular delta u and this equation is true. So I tell you, every human being has 2 eyes. Nicholas is a human being. How many eyes has Nicholas? 2 eyes. Okay? Do you know that my students tell me that Nicholas was born without 1 eye? So I cannot give an example of this logical deduction. Okay? So what can I do? I can tell you, every real number has a square which is positive. 2 is a real number, the square of 2 is positive. Okay? This is a form of logical deduction which is due to Aristotle. It's very old. Okay? So, I'm not using a particular case, I'm not particularizing. I have a general universal property. Something is true for every delta u. So, I start using some delta u's. So, I choose this particular delta u. By the way, COMSOL, ANSYS is using this procedure for calculating the equilibrium of a given beam or more complicated systems, because they are using test functions and they are minimizing, imposing this equal this for every test function in a given set of test functions which they are introducing. So this is not only a powerful theoretical tool, but this is also a powerful practical calculation tool. This is the process which is used by COMSOL or every software. Okay? But let's go ahead in deducing results from this general statement. So, I choose a particular delta u, these terms are vanishing, I'm left with this expression. The expression is integral of something, in this moment it is not important what it is, so I call it f of s, times delta u of s, and this has to be 0 for every delta u. So the poor Lagrange needed to solve this problem. I have a function f. This function multiplied times every function having 0 value with its derivative in 0 and having 0 value with its derivative in L, so times every delta u verifying some boundary conditions, the integral of fs delta us has to be 0 for every delta u. Can I tell something about f of s? Theorem of Lagrange. If f of s is continuous, then the only possibility is that f of s is 0. The only function, continuous one, which multiplies times regular functions delta u and integrated over an interval gives always 0 is the 0 function. This is not trivial. It is very similar to say I have a number a, I multiply it times x, and for every x this is always 0. What happens to the number a? It has to be 0. So the poor Lagrange needed to generalize this statement in this context. I have a function f of s which is suitably regular. This function multiplied times delta us for every delta us has to be 0. What can I deduce for the function f of s? I claim that this has to be 0. We can try to understand why this happens. The reasoning is absurdo. Assume that f is not 0 in a given point. So we take S0 and we assume that f of S0 is positive. Okay. Moreover, f of s is continuous. So the function has to do like that. You remember, there is a theorem, so-called permanence of sign theorem. If a continuous function is positive in a given point, then in the neighborhood of that point, it is continuous. It is positive. Okay? So the graph of the function f of s in the neighborhood of s0 is positive like that. Okay? Then I take this function delta us. Do you know how modern numerical analysts call this function? They call it the sampling function of x0. This is a function which is sampling s0. Is different from 0 only around s0. Now, the integral of two positive functions is positive. Cannot be 0. So why we obtained this absurdo result? Because we assume that fs0 is positive. So you need continuity of f and continuity of delta u. Okay. So painfully Lagrange understands that necessary condition for being this quantity equal to 0 for every delta u is that Km u second minus b of s is equal to 0. This is what is called the equation of elastica, the equation of Euler beam. Maybe you don't recognize it, but I will show you that you can recognize, you will recognize that it is equivalent to a form you have seen. Okay, if this quantity is 0, then all this integral is always 0. So I can erase this, and I get that for every delta u, this quantity is 0. Of course, I have erased too much, because I have here Km u second first delta u 0L, okay, which was there probably, right? Maybe I didn't apply Torricelli, or I don't know. You have seen that this term was there, okay? Okay. Now we have a delicate, but not so much delicate point.
Minus here.
Sorry, minus here, yes. Minus. I know the result. Minus. Minus here. It helps to know the result if you are wrong with the sign. Okay, so now we have another delicate point. I have 0 and L. Okay. What can I do? I can start with delta u, which is, for instance, 0 in L, but delta u prime, which is different from 0. So I can have a function which is doing this way. So if delta ul is 0, delta u0 is 0, this is not there, delta u prime L is different from 0, and I get Km u second in L equal 0. So now we must tell what we are studying. We are studying the clamped beam on the left with an applied force on the right with 0 couple in L. And we get that Km u second in L is 0, which means that you have no externally applied couple there. Okay, I'm using what you should already know in the subject. Okay. What happens in 0? U prime in 0 is 0. Delta u prime in 0 has to be 0 because you must verify boundary conditions. You must verify your kinematical prescriptions in 0. So this boundary condition is not telling you anything. where you have clamped your beam. Okay? I'm running on this because you heard already these things several times. Now, we are left with delta UL. So, our sampling function has to do this. You have a delta UL which is different from 0, but its derivative is 0. In this way, you get rid of this, and you get that Km minus Km u second first minus F is equal to 0. Or, if you like, F equal to this quantity. So, imposing that your energy is minimum in the equilibrium configuration gives you this ordinary differential equation for u and this boundary condition together with u second L equals 0. On the free end, while the clamping condition in 0 gives you u 0 equals 0 and u prime 0 equals 0. These are called essential boundary conditions because they tell you which are the boundary conditions which must be verified kinematically. You impose to your beam that this point cannot displace and the section cannot rotate, while this and that are so-called natural boundary conditions, which you obtain imposing the minimum condition. Now, do you think that you must ask to console that u second L is equal to 0 and this third derivative is equal to F? Console as an algorithm minimizing energy. You don't need to impose these conditions. They will be estimated by your code. Instead, you must tell to console that u0 is 0 and u prime 0 is 0, because you must tell to console that somebody is keeping this left side of the beam blocked without rotation. Otherwise, this beam can fall along F, attaining any negative value for energy. Okay?
Can I ask one thing? Does this sampling function remember to something we have discussed in these days? For instance, the fact that this has to be 0, the value is 1, does it remember to something we have discussed in these days? For finite elements.
Do you understand what Lagrange did? He invented the method of finite elements before the invention of computers. He even did not know that he was inventing this method. he was using mathematical logics for solving a problem. Okay, but now that you are understanding this, you must be patient and you must hear another at least 10 minutes of considerations, because otherwise we lose your effort. Okay? Lagrange did not know how to calculate the minima of functions of 500 variables, because he could not calculate 500 partial derivatives. So Jupiter is very upset against us. Do you know that Jupiter is the Greek god of the thunderbolt? Huh? So let us reason a little bit. Okay? If I have E total, okay, you have studied shape functions and you have decided that you wanted to find U of S as sum over n of a n phi n of S, where phi n are shape functions. Okay, I don't know if you have called them phi n. Yeah? So what you have done, you have not done it by hands. You have said that console is taking this expression, which is an approximate. Imagine that you have a powerful computer, as we have now. So instead of doing all this integration by parts, instead of obtaining this differential equation with these boundary conditions, so instead of developing the theory of Lagrange theorem, first variation of a functional depending on a function, okay, instead of doing all this, you are lazy. You say, I have a powerful computer. I don't need to think. I write US equal this summation, then I calculate the second derivative of this, I place inside the expression of E total, and this becomes U function of A1, A capital N. So I have a function of capital N variables. I calculate all the partial derivatives of this. I equate these partial derivatives to 0, and I get the equations for A1, A2, AN. Okay? I don't need to think, because I simply replace this expression inside that. Okay? Now, I don't know who among you asked me about locking. If I don't choose phi n in the right way, I don't get the right result. Why? Because if phi n are linear, I calculate the second derivative, I get 0. So E total is 0. and I cannot minimize anything. You understand this point? If I have integral of u second, and I've chosen phi n of s piecewise linear, I calculate the second derivative of a piecewise linear function. What I get? 0. So I get everything. I get nothing. I get what I want. I pay and I can get everything. So the choice of this phi n of s must be adapted to the energy functional which I have in my hands. This is the first observation. The second observation is the following one. If n is 200, I must calculate the solution of 200 equations in 200 unknowns, and I cannot do it by hands. This is the reason for which Lagrange developed the reasoning I gave you before. Now, can I solve this by hand? I must calculate the primitive of Bs. Then the primitive of the primitive, I must calculate 4 integrals. For each integral I calculate, I need an integration constant. So I need 4 integration constants. I have 1 condition, 2 conditions, 3 conditions, 4 conditions. Exactly as many boundary conditions as integral constants I have. The development of civil engineering of 19th century is based on this solution of our problem by Lagrange. Because without computers, they could calculate the equilibrium shapes of complex systems of structures. So let us move another step. So the method which was useful in 19th century, write this equation, find the boundary conditions, solve by integrating this system of equations. This method, very useful and very powerful in 19th and 20th century, now is completely obsolete, simply because we have computers. So follow the point of view of somebody as I am, who must choose what I should teach to young generation of students. Should I directly write you these equations, trying to deduce them, postulating balance of force, balance of momentum, and then solve you with the ancient method some equilibrium problems? Or should I teach you the principle of minimum of energy and try to show you that these are equations which can be deduced from the principle of minimum of energy? Which are the tools used now for finding engineering solutions? Nowadays we are using computers for finding the solution of engineering problems. So we must teach you this method, finite elements. And finite elements is using the principle of minimum of energy. In other words, the basic principle postulated by D'Alembert, since Archimedes of Tarentum is the most basic principle on which we base our understanding of nature. While these equations became popular in a given historic period and now are obsolete. So one has to choose those principles which has proven to be more stable in time, and one should avoid to give you a partial vision of mathematical modeling. So this is the reason for which I think we must start always from the principle of virtual work. Okay? Okay. Now, let us try to make a plan for the future. I want to organize some lectures for you in which I deduce the equilibrium of a three-dimensional body, the equations of equilibrium of a three-dimensional body, starting from the minimum of energy, while probably even will teach you how to find the evolution equations for a beam, starting from the principle of minimum of action, in which you introduce kinetic energy together with deformation energy and total external energy. The idea is to prove that everything can be found minimizing something. More difficult, I don't know if we have time, for sure for master students we will do it. We will show you that also dissipative phenomena can be described using minimization principles. Okay? I hope we will send you the message. And I hope that you will understand better the numerical codes which you are using once you have understood that everything is variational. You see, there is no numerical code solving this. Numerical codes look for minima all the time. Okay? Okay.